Hello everyone, welcome back. I hope your preparation is going well, and if it's not preparation, your studies are going well. So, we are discussing econometrics over here. So, we've been trying to get across some concepts of econometrics, and today we'll just move ahead on the same track. Okay, so today we'll be talking about your standard errors of least square estimators. Okay, estimators. So standard error is basically a standard deviation. So since we are doing repeated sampling, okay, so we are taking multiple samples, and through those samples we are calculating your or estimating your beta 1 and beta 2 by different values of beta 1 hat and beta 2 hat. Okay, so since we are getting a large number of these values of these statistics, okay, like from every sample I'll get a set of beta 1 hat and beta 2 hat. Okay, similarly when I keep on doing this for multiple samples, I'll have multiple values. Okay, so since there is a set of values, so I am interested in calculating the standard errors or the standard deviation. So my values, or from every different sample, whatever values are of beta 1 hat and beta 2 hat I'm getting, they should not fluctuate in a very big range. Okay, so the range of fluctuation should not be high, the deviation should be small. Okay, so that is the reason, or that is the reason why your standard errors become important here. Okay, so having a knowledge of standard errors is really important. So we'll try to calculate, or we'll try to see how we can calculate the standard errors. Okay, so we know that least square estimators are a function of the sample data. We have seen this in the previous videos and in the formulas that we have talked about. But since data changes from sample to sample, the estimates will also change. Okay, in every sample I'm getting new estimates of beta 1 hat and beta 2 hat. Therefore, since the value is changing, there should be a measure of reliability or precision, or how close the values are, okay, to the actual values of values of beta 1 hat and beta 2 hat that I'm getting. Okay, so in statistic, precision of an estimate is measured by standard error. Standard error or the standard deviation. Okay, so variance of beta 2 hat can be written as sigma square, okay, upon xi. This is small xi square. So we have seen what small xi represents. Okay, so standard error, sorry, not standard years, standard error of beta 2 hat becomes your sigma upon summation xi square. So your standard error is basically your under root of the variance. Okay, similarly for beta 1 hat, summation x, this is capital X, xi square upon summation small xi square into n. This implies standard error of beta 1. This is beta 1 hat. So the notations are very confusing at times. Okay, so just be very precise and be more attentive when you write the. So this is your entire thing is in under root. Okay, summation xi square, right? So these are the formulas. So in these formulas, I know what xi is, I know what capital Xi is. Okay, this is coming from the sample that I've taken. So the xi values I'm getting from the sample. So these are the familiar term to me. But what I don't know is sigma square. So we will estimate this. Okay, estimate this value. So how do we do this? So your sigma square can be estimated using your estimator, which is given by uy hat square upon n minus 2. Okay, so from this I can estimate this, and using this I can find the variance of beta 2 hat and beta 1 hat. Okay, because this is required, this is the term given in the formula. Your n minus 2 or the denominator here. So why are we using n minus 2? So there's a concept called degree of degree of freedom. Okay, so let's understand this, what this means. So your degree of freedom is basically your total number of observations, total number of observations in the sample, in the sample, which is n, suppose, okay, minus the number of independent independent constraints put on them. So in here, when I'm estimating sigma square, okay, so I in order to calculate this value, I am dividing this by n minus 2. Why? Because in order to have this knowledge, I'll need the knowledge of your ui hat square, and for that I'll need the knowledge of my beta 1 hat and beta 2 hat. So my calculation, my this calculation of sigma hat square is limited by the values of these two parameters. So before I calculate this value, I'll have to calculate these values. So my number of values, okay, which actually are n, but they are restricted by these parameters. Okay, so until I have these values, these number of n values will make no sense to me, because I will not be able to calculate the value of sigma hat square. So this is what degree of freedom means. So your sample observations being restricted by the number of parameters or independent constraints that you have to calculate. Okay, so that is why we use n minus 2 here. I hope this made sense. So now I know how I can calculate your sigma square by estimating sigma hat square. Okay, so sigma hat square is the estimator of true but unknown sigma square, and n minus 2 is the degree of freedom. So let me just write this down. Is the estimator of true but unknown sigma square. So we through sigma hat square, we are, it is an estimator of the true sigma square, but we don't know this value. Okay, we are just trying to estimate it, and n minus 2 is your degree of freedom. Minus 2 is your degree of freedom. Okay, and summation ui hat square can also be called as your sum of residuals squared. So ui is the residual, okay, and when I square it, it is called sum of residuals squared, or residual sum of squares. So this term will be used in the upcoming video. Okay, so let's see, can we create something else here? So supposingly I have ui hat square is equal to sum of minus beta 2 hat square into summation xi square. This is your capital Xi. Okay, so basically it is, so from here I know that beta 2 hat is equal to summation xi yi upon summation xi square, and this implies summation ui hat square is equal to summation yi square minus summation xi yi whole square upon summation xi square. So this implies sigma hat is equal to your summation ui hat square upon n minus 2. So this is called the standard error or estimate or the standard error of the regression. Standard error of the regression. So this is coming from this formula also. It's the same thing. So we have taken just the under root of this only, and we have written it in terms of your under root or your standard error form. So let's move ahead. So it is basically the standard deviation of y values about the estimated regression line and is often used as a measure of goodness of fit. So the formula just that we just saw here, this formula, this formula, this one. So it is basically the standard deviation of the y values around the regression line. Okay. So this is your regression line and the values are distributed around this line. So it is measuring the standard deviation of these values, these y values, okay, for respective x values, okay. So it is also often called the measure of goodness of fit. Goodness of it. So we'll talk about goodness of fit. So in very simple terms, it is basically how well your regression line is fitting in the data in such a way that the errors around the regression line are minimized. Okay, so this is the distribution of the y values, and you have to fit a line, regression line, in between this data, and you have to do it in a way that it minimizes the error around the regression line. Okay, so we'll talk about goodness of fit in the next video also. So this was about your standard error of the estimators or the least square estimators. Okay, so a few features of variance of beta hat and beta hat. So the first one is that the variance of beta 2 hat is variance beta 2 hat is directly proportional to sigma square, but inversely proportional to xi square. So we can see this from the formula itself. So it's very evident from there. So that this means that given sigma square, the larger the variation in the x values, in these values, if there is a lot of variation in the x values, okay, the smaller the variance of beta 2 hat, and hence the greater the precision with which beta 2 can be estimated. So if I have x1 x2 x3 x4, okay, if the deviation or there is a huge difference in the values of x1 x2 x3 x4, it means that this value will also be high, and it means that the variance of beta 2 hat will be lower, and the estimate would be more precise. Okay, so this is a good thing. Okay, also as n increases, the number of terms in summation xi square, okay, in this summation of xi values, okay, if the I or the n is increasing, so this summation is rising, and this will also affect the estimate, because then also the variance will decrease, and the estimate would be a good estimate of the uh, real beta 2 or the real parameter. So these are some features. So basically we are taking some interpretations out of the formula itself, how what things actually mean. So we have seen the formula and what is the uh, meaning of that formula, what is that formula trying to express. Okay, so this was all in this video. So see you soon in the next video.